Let's begin. So the last part of the discussion of this chapter on the discrete stochastic processes is going to be on functions. Markov processes, a very important class of processes. Very the kind of processes that we are going to deal with throughout the course are going to be the Markov type processes. In the book, you find them defined very abstractly. You can read it for yourself. But since this is the first exposure to the Markov processes, I would like to kind of give you a more visual, a more concrete kind of description of the processes. And you may read it from the abstract version as well. It's not that difficult. So we know that the crucial assumption for central limit theorem and say for example law of large numbers is this, that the stochastic process that you have or the sequence of random that you have must be ideal. That's what the crucial assumption is. But what did Markov said? In other words, what are these theorems are, the law of large numbers and central limit theorem tells you that if you have a sequence of random variables or a stochastic process in which the random variables are IID, then you can talk about their long-term behavior. Okay? So if you want to study a stochastic process in long run, in other words, how does it going to behave in long run, you need to have an assumption of being IID active. So what did Markov show? Okay, that's not the case. You can still study, the long-term behavior of a stochastic process. Okay, when there is the notion of dependence and like. So that's what makes that kind of very interesting kind of processes. Huh?
There will be some other payoff for this thing.
Yes, there will be always some other payoff, but what central limit theorem and law of large numbers kind of means is that you need to have IIDs, which is a kind of a stronger assumption. Okay, so if you want to know the long-term behavior of the process, you need to have the information of being identically distributed and independent. Markov showed that you can consider a class of functions in which you don't have not necessarily the assumptions of IID. We still study their long-term behavior. How this process is going to be in long run. So let's start. So whenever we are talking about, say, for example, discrete time is Markov processes, called the Markov chain, cycles. So very widely applied kind of processes actually. Examples are processes that we will be mostly interested in actually. So I'll talk about it, some of it and some of examples of it today. So the Markov chain, describe the Markov process. You need to have a state space. So a state space is a set of the values that the process can take actually. So by state space we mean the set of the values that the stochastic process can take. So we can use an abstract notation, but usually will denote the state space by the set of natural numbers. 0. Okay, so 0 is not a number here, but a state. So process can be in state 0, 1, and it can go from 1 to 2, and 2 to 1, 1 to 3, and 3 to 1. So, all these are states. Okay, for example, what do you mean by, so one of the manifestation of a state could be so the weather. So we know that weather can be in different states, especially when you are kind of places where the weather is really unpredictable. Okay, so you have no idea that okay, in the morning if it's dry and what's going to happen after the 1 hour. So maybe the weather can go from dry to wet, to be from wet to be hot and hot to hot, cold and so on and so forth. So the hot, cold and wet and dry, they all are the states actually. Okay? Of of weather. When weather is the state of the weather. The weather has roughly a stochastic process actually. Okay, so what could be the other example? There are many examples actually. Okay. So imagine you are playing, say, a game. Okay, it's a gambling game actually. Then your gains can be in a state actually. So imagine that you are, playing a game in which you are saying that okay, on every game, so on every round of coin tossing game, you are let's say either losing $5 or winning $5, $3. Okay. Then you know that your gains would be a number actually. So in this example, that the notion of the state would be that okay, how much money that you earn, $5, and $10, and $15. You can lose $5, $10, and $15, and you can gain say 3, 6, and 9. You have no idea that sometimes you will lose, sometimes you will gain. So each of the interpretation, the amount of money that you're going to have in your pocket office is going to be one of the state. Okay. So by a state, you mean that the process, especially for Markov chains, the values that process can take, the variables can take. So this state can be a finite set as well. Okay. For example, you are in Sukkur and for your favorite food, okay, you have what? You have, say for example, 5 restaurants. So then you want to do some shopping actually, then clothes or something that you like. Okay, there are 5 to 6 shops available. So what you're going to do? Okay? So what customers are going to do basically, they are going to switch between the shops. Okay? But in this case, like shops are the states. So they are like the states and people are going to switch between the states. Okay? That would be a state space, but which is kind of finite. So state space can be finite, state space can be infinite. That's an abstract notion. Okay. You can interpret it the way you like. Basically, like x naught, x1, x2, xn, however, obviously very different. Numbers, it must be a discrete. So obviously, when we'll talk about, for example, GDS time Markov chains, this would be an interval rather than be the discrete setting. Okay. Let's take one example and let's see. So consider you are playing a game, okay, of coining, you are tossing the coins repeatedly, okay, and if heads comes up, then you pay, for example, say $1, and if tails comes up, you pay $1 and get $1. Right? And imagine that, okay, so basically this relate between people, okay, so that's me and that's you, say $20, you have like $50 actually, okay. So what could be the potential state space, for example, for me? So what would be the state space for me at
0
in such a situation?
no mean.
In the new ones. So in other words, so one situation can be that I lose everything. So in that case, I can be in a state of being zero, actually. Or I can lose everything except $1. And what will be the the luckiest situation actually that when I win everything? $70. So state space that I and you both can be at. So this is like a random walk. It's nothing. It's a random walk. And what we can prove basically is an example that one of me or you, or one of the person is going to be doing that too, no matter what happens. Okay. And the person who has less money, there are high chances that is going to go empty-handed. Okay. And the more money you have here, for example, if your opponent has more and more money, you will have less and less chances. Therefore, we also say that don't play with the casino. So what we can actually show that by applying very simple principles of Gambles' theorem that the casino has infinite amount of money. It's not really infinite, but it's huge in our case actually. Okay, so no matter for a time being you may win some money, okay, but since you have a finite amount of money, okay, and the other has roughly infinite amount of money or a huge amount of money as compared to you always be doing that. You have to lose no matter how hard you plan. So another example that I quite often give is this game of something that I was a few years back I played a lot. It's what do you call it? Subway Surfers. Okay. So you have this game Subway Surfers. So if you say that this kid that is running from police due to the graffiti that is going on the trains, okay, can be in two states. So what could be the two possible states? So either you are caught up, okay, or you are safe. Okay. But this is like very much analogous to it. Either you will be caught or you will be safe. But we know that no matter how hard I try, no matter how big expert I am, I'm gonna caught up eventually. Why is the case? Because the track is infinite. It's not gonna end. Okay? So your opponent So it has more and more possibilities, okay, of catching you up, and eventually you will. So playing with the casino is a dangerous choice. Maybe in such game you can have maybe optimal chances, some chances that they have win 15 points. But if this amount would grow more and more and more, no matter how much money you have here, you will always lose. Okay. Anyway, so would be all these are examples of something what we call the random walk. So let's begin our discussion with random walk, and I'll quickly write the definition. What do we mean by Markov chains? Let's start with. Suppose I have a process X that I'm observing at the time 0, 1, and up to say n minus 1. Okay? And so that's what I have observed. And I would like to make prediction experiment. Okay, so kind of I have played n minus 1 games, coin tossing games. So I have all information at that time, and I want to make a prediction that what's going to happen next. Okay. So what we can say. So how does the plot of it goes on actually? Plot value. So it could be something that you have seen quite a lot previously. Process that. Something like that. Discrete time, that's a linearization that I have done, for example. Something like that. So what I am interested in, and maybe I can assume that my gains, whatever quantity that I am interested in, okay, so my loss or my wealth can take what value say it can take these values. That's not x1 and after say xn minus 1. These are the observed values that I have. It's not x1 and x2 and xn minus 1. It's like the money that I have in my pocket after the n minus 1 gives. So I would like to make a prediction. What is the probability that on nth game I will have this much amount of money? Given that, I had initially x0, and after the first round I had x1, and so on and so forth.
xn
minus 1. So this is what that I'm interested in. But I know that my xn minus 1, for example, if I am playing $1 game actually, could be what? So it could be my previous money plus 1 with the probability p, or the previous money minus 1 with the probability p. So this would be one of the two possibilities. Okay. So what you can say that this guy, so what will be this probability? So you're going to say this probability can be xn minus 1 plus 1, okay, with probability p, and xn minus 1 minus 1 with probability 1 minus 1 and 0 otherwise. So in other words, there is no chances that you're going to lose more than $1 or less than $1. Okay, so otherwise. Okay. That's now. What do you think? What would be the probability of xn given xn xn? What would be the probability that you're going to get xn as your gains are going to take value xn, given that xn minus 1 was xn minus 1? What do you think? What would be this probability? In other words, what we can say that this probability would be precisely the same. Okay, precisely the same. So what follows from here, that all this information except this part doesn't matter. Okay. So if n minus 1 is like my current state, it's now, and all these previous timings are what do you call past, okay, and xn is future, then what we can observe in this case is that the probability of the future, given that you have past and the present, is same as probability of the future, given that what you have now. So the previous information doesn't matter actually. So in other words, so that's a kind of a process which is kind of memoryless actually. So in other words, if I am here, so if my gains are here, so they are going to be where I have no idea. It has nothing to do with what previously has happened.
Sir, I have confusion here. We have defined random variable that is taking two values.
Right.
After computing its probability,
Right.
again it's turning out to be same. Means the value that random variable.
Okay, sorry. Oh, no. Doing something stupid. I should have write p here, 1 minus p and 0, and I say if xn is if xn is should say xn is xn minus 1 plus 1, and if xn is xn minus 1 minus 1, and otherwise let's set this
Same.
so that these are, so this is probability, should be probability, right? Okay, and you can have the precisely same thing here. This xn is xn minus 1 plus 1, and 1 minus p, so xn is xn minus 1 minus 1 and 0 otherwise. Okay. So what's a Markov chain actually? That's just one example of it. The Markov chain must write on green ruler. This should be a plus. The Markov chain is what? So it's a stochastic process that is memoryless. Stochastic process is memoryless. I can model a hell lot of things actually. So, it's a definition. So imagine so process xn is Markov process, okay, Markov chain, if following thing happens, okay, these xn takes values in some state space, okay, some state space S, which we have already defined set actually. which can take the potential values, where the process can take values.